In this video, we're going to be exploring trig ratios in context. Specifically, we're going to look at angle of elevation and the angle of depression to objects. So in this diagram here, we have an observer. And this observer is seeing two different objects. One object, the observer has to look up to see, and another, the observer has to look down. In the one that the observer has to look up, the line of sight, your normal line of sight, is just going to be straight across horizontally. In order to see this object, the observer has to turn their head up, or their eyes at least. That angle that's formed from the normal line of sight to the site where we can actually see the object is called the angle of elevation. Here, again, our normal line of sight, the object is down below. The angle that's formed from the normal line of sight to the object that we actually see, that angle that's formed right there is called the angle of depression. So the angle of elevation and depression are going to be very important for us to be able to figure that out, because then we can solve some of these trig problems. Here we have a hot air balloon, and we've got a person down on the ground. They're observing this hot air balloon. We've got a horizontal line, which is the normal line of sight, but we also have someone in the hot air balloon that's observing the observer, if you will. So they've got your normal horizontal line and then another angle that's formed here. We want to angle the angle of elevation from the ground observer is E, and the angle of the depression from the balloon observer is D. So this would be E, and this would be D. The angle of elevation is measured from the horizontal line up to that line of sight, whereas the angle of depression is measured from the horizontal line down to the line of sight. What's the relationship between them? Well, the fact of the matter is horizontal lines are going to be parallel. We know those are going to be parallel. We also know then that these angles right here are alternate interior angles, so therefore they must be the same. So the angle of elevation and depression are congruent. And that has to do with parallel lines and alternate interior angles. Do a couple of basic examples, and then we'll get to some of the more complicated where you might have to have multiple triangles in one. So in this first one here, we have an angle of elevation from the ground to the kite is 52 degrees. The length of the string holding the kite is 100 feet. Determine how high the kite is flying off the ground. So we have the picture already set up for us, which is nice. We can then look at that 52-degree angle and start labeling our sides. So here we have our opposite side, our adjacent side, and our hypotenuse. We're trying to find the height of the kite off the ground. So I'm trying to find the opposite side, and I know the hypotenuse, and I also know that angle that's drawn in at the bottom. That's the angle of elevation, because again, the ground is your normal horizontal line. That kite string's going to form that angle with the ground. So we're going to set up something involving an opposite side and a hypotenuse. That sounds an awful lot like a sine to me. So sine of 52 degrees equals, if we call that x divided by 100. And again, we can treat this as sine of 52 over 1. Cross multiplying, we have x is 100 sine of 52. So let's find out what that is. We're going to type in 100 sine 52. And I get 78.8, rounding to the nearest tenth of a foot. On 5, we have a lighthouse keeper spotting a boat out on the water at an angle of depression at 27 degrees. The tower is 120 feet tall, so I'm going to write that in there, 120 feet. Determine the distance of the boat from the lighthouse. So this is what we're trying to find. Now we have a couple options here. The fact is I can use that 27 if I want, or I can set something up slightly different. I want to make sure, first of all, I understand that the angle of depression is in the correct spot, that it's not this angle here, it's this angle. Because the normal line of sight of the lighthouse operator, the lighthouse keeper, would be this dotted line right here. And they have to look down to see the boat. So this line here and the line of sight have an angle of 27 degrees. That's why the depression goes there. And it's generally going to be outside of our normal triangle that we're going to set up. Now, we have an option. One option is I can set this up as 27 degrees also, because I know the angle of elevation and depression must be equal. My other choice is to find out what this equals. So if I can find out what this equals, I have 90 minus 27, and that would be 63 degrees. So we're going to take 63 degrees, and we have this side and this side. So this is my opposite side and my adjacent based on that 63 degree angle. So because of that, I'm going to use my tangent. Tangent of 63 is the opposite, which is x, divided by the adjacent, which is 120. Again, that's over 1, so cross multiply. X is 120 tangent 63 degrees. All right, let's type it in the calculator. So 120 tangent 63, 235.5 feet. So that's some basic trig and context. Let's do a more complicated one involving Mount Rushmore and George Washington's head. So a tourist is visiting Mount Rushmore, is standing 500 feet from the base of the mountain. The tourist measured the angle of elevation to George Washington's chin as 45 degrees. The angle of elevation to the top of Washington's head is 48.2 degrees. We want to know how tall is George Washington's head, and round our answer to the nearest tenth. We're going to need to set up two triangles. One of them is going to have an angle of elevation to the chin, and one has an angle of elevation to the top of the head. So let me set up a first triangle here. Let's pick red, and that'll be to the chin. So we've got this first triangle here. So our observer is going to be 500 feet away from the base of the mountain, so we'll call that 500 feet. And we are going to measure this, and the angle of elevation for that first one is 45 degrees. And what I want to know then is how far is his chin from the ground? So let's call that x. So again, at my 45 degree angle, I've got my opposite and adjacent, that's the tangent. So the tangent of 45 degrees is x over 500. So x is 500 tangent of 45. And the calculation would basically just give me that that was 500 feet. Okay? But I then want to figure out what's the angle of elevation to, or I'm sorry, what's the height all the way to the top of the head. And so to do that, we're going to draw a second triangle. So our base is still going to be 500, so that's not going to change. So I'm just going to kind of like color right over it. Except now we're not going to go to the chin, we're going to go to the top of the head. There we go, close enough. And then we're going to draw in our missing part there. This angle is 48.2 degrees. So a lot of the same things that we have are going to be exactly the same. Instead of x, I'm going to call this y. We still have that 500, so now our setup is going to be tangent of 48.2 degrees is the opposite side, which is y, over 45. Again, that's over 1, so I can cross multiply. I'm going to multiply 45 times the tangent of 48.2. And I get 50.3. Oh wait, I'm sorry. I don't know why I put 45. That should be 500. All right, it's going to make a significant difference. All right, let's try the 500 tangent of 48.2. That's better. 559.2 feet. So the 500 measures from the ground to the chin. The 559.2 is from the ground to the top of the head. So the difference between those would be the height of George Washington's head, which would be 59.2 feet tall. So if you ever go to Mount Rushmore, you can verify that these measurements are actually true using some trigonometry.